Hello and welcome to everyone. Today we will be discussing the 30th lecture of the course on the financial econometrics. In continuation with the last few classes, today we will be also discussing about the two models, that is ARMA and ARIMA model of the univariate time series modeling approach. So in the last two classes we have discussed the autoregressive process or autoregressive model and the moving average model. So today we will discuss the combination of these two, that is the ARMA model. So what we know here that ARMA stands for autoregressive moving average model. So we have discussed that we can represent a series using the autoregressive process of infinite order, or we can have the moving average model of the infinite order. However, estimating the infinite parameters in autoregressive process or autoregressive model, similarly in the moving average model, is not desirable. What we call is basically the parsimony, the principle of parsimony. That means we wanted to have as much as possible the least parameters into the model. Otherwise, we do face the problem of degree of freedom, then the estimates will not be that much reliable. So we always try to, in the modeling approach, that to have as much as minimum number of parameters. However, the fortunate thing is that, fortunately we have an option that in such cases where the autoregressive model is of infinite order or the moving average of infinite order, but what that solution we have? That solution basically comes in the form of autoregressive moving average model, where basically we combine the autoregressive model and the moving average model to bring a parsimonious model here. So to try to understand what we mean by the autoregressive process, let us take a case of cells. So let us say any particular cells of any particular goods is taking place like this. So let us say we have here, this is the cells which follows a stable process. Then there's a two thing may happen. Let's say the company has started a campaign for the advertisement of their products. So obviously at time t when the advertisement has started, so the sales may jump. So it may jump like, let us say like this. So this jump is nothing but the random. So what we call this would be represented by the UT. And the effect basically will have in the next period, it will have more effect. So let us say this we have like this. However, after a certain period, the effect may come down. However, there will be certain kind of brand loyalty, or the product has people are comfortable with that product, or that they wanted to consume that product. There will be certain people of that. Then in that case, basically this, what is the sale we have here, the next period the sale will depend on this period. So this will be the process where it depends on the previous sale. So however, here we will have this jump in UT, and ultimately this UT will realize. So this component, this part is nothing but what we have, this sale depends on the previous sale. However, in this case here, it depends on the UT plus the previous advertisement campaign. So that means this whole process follows to structure, that is one what we call the autoregressive structure, where the current year's sales do depend on the previous year's sales. Then this part where basically it follows an moving average process, where the campaign has been introduced, it has have the positive effect, but that positive effect will not be continue. So in the next period there will be effect of that campaign. However, that will be keep on decreasing and decreasing. So that means this introduction of campaign we can treat is as the error term. So in this case we will have this. So this is the basically what we wanted to plan here. This is nothing but an example of combination of these two, that is autoregressive and moving average process. So this is the real. Then you may have the other examples also. For example, let us say in any country, it has its reputation based on the macroeconomic variables. Let us say in the financial market, based on the conditions of financial markets, based on the condition of the economy, the financial market perform. So where the current observation or the current performance of the particular company or the particular economy do depend on the previous conditions. So it follows the autoregressive structure. Let us say there is some kind of shock. For example, for a particular company, that may be the merger, or maybe the acquisition, or maybe the new investors comes, then that may have a positive effect, but that positive effect will not be always continuous, which plays the role of error term or the shock. For economy, let us say there is the terrorist attack, or let us say there is some kind of a natural calamity which may have the create a shock, but that shock will not be permanent. So the effect of this shock will be less and less as time passes. So that part, it basically plays the role of moving average structure. On the other hand, the other part plays the structure of the autoregressive process. So for such kind of phenomena, neither the autoregressive model or the only moving average model will be able to capture the whole situation. So in such situation, the ARMA, that is the mixture or the combination of autoregressive and moving average model, is better than the individual autoregressive or moving average model. So let us say what we have basically here. So in this case, these are the two combinations of this. So data has to be stationary, as was the case in case of moving average and autoregressive process. So here, since let us say autoregressive is the order of P and the moving average is of order Q, then the ARMA will have also order of P and Q. For example, we can write here ARMA PQ. Let's consider the ARMA 1 1, that is the autoregressive part has the order 1 and the moving average have order 1. So in that case, we can write yt is equal to phi 1 yt minus 1 plus theta 1 ut minus 1 plus ut. So this structure is basically for the moving average, and this structure is for the autoregressive process. So that is the current observation of the series depends on the previous observation plus also on the previous random shock or the random error. So using the lag operator, we can write this equation in this particular form, where the yt minus 1 has been replaced the lyt, or we can write yt minus phi 1 lyt, or we can write this 1 minus phi 1 L into yt is equal to 1 plus theta 1 into L. So this is nothing but basically in form of lag polynomial. Similarly, we can write ARMA 2-2 model, that is we can construct this model like this, and similarly we can have a ARMA PQ model in the generalized form. So in the generalized form, it will have like this, or we can write yt is equal to phi I yt minus 1 up to P plus theta 1 theta I ut minus I from I1 to Q plus ut. So this is the concise form of this structure of ARMA PQ model, that is ARMA of order P and Q. And the lag polynomial form we can write like this here. So let us discuss what are the properties of ARMA model. So when we say properties, basically we wanted to have the theoretical statistical properties of the autoregressive moving average model. So we know that ARMA 1, let's start with the ARMA 1 1. So we can represent this in this form. So using the polynomial equation, it may be written as phi L yt is equal to mu into theta L y LT. So here phi 1 is not equal to 0 and theta 1 is not equal to 0, and mu is a constant term, that is the long term mean of this process. And we are assuming that expectation of ut is equal to 0, expectation of ut square is sigma u square, and there is no autocorrelation between the error terms, or we can say there is no autocovariance or correlation between the this UTs. Or we can say the UT follows basically a white noise process with mean 0 and variance sigma square. So this can be written in this particular structure form. So what we know that the properties of an ARMA 1 basically is the mixture of those of an AR1 and MA1. So the stability stationarity condition is one of the an AR1 model. So we have discussed already a autoregressive model where we have proved that to be stationary the parameter theta 1 in absolute value must be less than 1. Similarly, we have proved the invertibility condition that for MA1 model the absolute value of theta 1 must be less than 1. So let us see in this case what are the what properties we have. So mean, if we can write expectation of yt is equal to mu upon 1 upon minus phi, and variance is equal to variance of yt is equal to expectation of yt into yt. So this mean is basically from where we got it. So we write the ARMA model as, so we write the ARMA model yt is equal to mu plus phi 1 yt minus 1 plus theta 1 ut minus 1 plus ut. If we take the expectation of yt, so expectation of mu plus phi 1 expectation of yt minus 1 plus theta 1 expectation of ut minus 1 plus expectation of ut. Now we know that expectation of this will be equal to 0 and this will be also equal to 0, and here what we have, expectation of yt is equal to, this will be mu plus phi 1. Now we know that expectation of yt and yt minus both will be same. So instead of expectation of yt minus 1, we can write expectation of yt, these two terms becomes 0, or here we can write that expectation of yt is equal to 1 minus phi 1 is equal to mu, or we can write expectation of yt is equal to mu upon 1 minus phi 1. So that's what here we have got. Here the phi 1 is nothing but the associated coefficient of yt minus 1. Similarly, for variance, what we know, for the variance we know that variance of yt is nothing, expectation of yt into yt, that is the covariance of between yt at, that is at lag s is equal to 0. Therefore we do represent using the gamma 0, that is autocovariance at lag 0. So in that case, using the similar approach as we have done in the case of autoregressive and the moving average process, we will get the variance of ARMA process is 1 upon twice phi theta plus theta square 1 minus phi 1 square. Here this is the parameter of t minus 1 and here it is ut minus 1. Similarly, what is the autocorrelation and autocorrelation function of the ARMA 1 model? So autocovariance gamma 1, so that is basically covariance between yt and yt minus 1, which using the same process we will get that this phi 1 plus theta 1 and phi 1 into theta 1 and phi 1 square. So this is basically, this phi 1 is nothing but the coefficient of yt is coefficient of yt minus 1, and this theta 1 is the coefficient of ut minus 1. So autocovariance gamma s, for the as lag s we have write this phi s minus 1. So here phi 1 s minus 1 and gamma 1 when the s is more than 1. Why we put the absolute value? Whether s is 1 or minus 1 or plus 1, in both cases we have the same autocovariance, the autocovariance structure will be symmetric. So whenever this gamma S is more than 1, we will have this particular structure of the autocovariance. Now what is the autocorrelation? Autocorrelation structure will be like this. When the S is equal to 0, we will have 1. When if S is equal to 1, then gamma 1 is equal to gamma 0, and similarly for this we will have phi 1 S to the phi 1 to the power S minus 1 into tau 1. So tau 1. So this will be the structure of the autocorrelation function. So the autocorrelation function of a process exhibits an exponential decay towards 0. So it does not cut off but gradually dies out as S increases, the same as we have in the autoregressive process or autoregressive model. The same the property will be exhibited by ARMA 1.1 model. The autocorrelation function of ARMA 1.1 process displays the shape of that in AR1 process when S is more than 1. Partial autocorrelation function of ARMA process will gradually die out, the same property as the moving average model is performed. So the autocorrelation function of ARMA 1 process exhibits exponential decay, it does not cut. Then we have another extension of ARMA model, what we call the ARIMA model. So basically ARIMA stands for autoregressive integrated moving average model. So basically what we know that this is the combination of AR, autoregression moving average model, with the order of integration, that is the non-stationarity into the series. A non-stationary can be made stationary by differentiating, that is we can have, let us say xt is a non-stationary series, then we can make it difference and let us assume that is nothing but the yt. So the non-stationary series was xt, we have made it difference to make it stationary and the name that series as yt. Then if the yt is follows an ARMA PQ process or model, then the original series, that is the xt, will follow an ARIMA PDQ model, where basically D stands for the unit root it contains. If it is 2, then the value of D will be 2. ARIMA is basically extension of the ARMA model for the non-stationary series. In that case, so let us consider we have ARIMA 1.1 model. So then we can write that delta yt phi 1 delta yt minus 1 and theta ut minus 1 ut. So this will be the structural equation, representation equation of the ARIMA 1.1 model, where the order of integration is 1 and the order of autoregressive is also 1 and the moving average order of moving average model is also 1. Then we can write ARIMA 1.1 as in this particular structure, or in the lag polynomial form we can write 1 minus phi 1 L into delta yt is equal to 1 plus theta 1 L into delta ut. We can similarly generalize this ARIMA model in this form. So if ARIMA 1.0.0, so that means basically it is an AR model of order 1, or if you write ARIMA 0.0.1, that means it is nothing but the moving average model of order 1, or if you write ARIMA 0.1.0, it is nothing but a pure random walk model, which already we have discussed in the beginning of the univariate time series modeling. So here basically yt is nothing but ut. ARIMA 0.0 basically cannot be applied in this situation because this will be a non-stationary, cannot be applied in this particular case here if the data is non-stationary. So in this case we will not be able to estimate this AR basically. And similarly ARIMA 0.1.0, which is nothing but the pure random walk model, then we will have yt is equal to ut. So let us visualize the AR, MA and the ARMA structure in this case. So let us say here we can see because the phi 1 is less than 0.7, so that means the data is stationary, and we can model this using the AR1 model. So if it is the AR1 model, then we can see here the ACF does not cut off, rather than it is decreasing towards 0 and here. However, here we can say it lag 1, we have only one PACF. So that means the cutoff of PACF is nothing but the lag. So we can see cutoff of PACF guides us the order of AR model. Similarly, if we see MA1 model, so here we can see in case of MA1 model that ACF it lag cuts off, and after that it becomes equivalent to 0. However, the PACF basically fluctuates and it moves towards to 0. So that means in case of MA model, the PACF decays towards 0, however ACF cuts off or we can say breaks off at the order of MA model. So the non-zero values of ACF guides us what will be the lag of MA, what will be the order of MA model. Similarly, if we see the ARMA 11 series, what we can observe here, it follows the similar kind of pattern here, that ACF follows the structure of AR process or AR model, whereas the PACF follows the structure of an MA model. So that's what we discussed earlier. The properties of ARMA basically is derived from the AR and MA model. So let us quickly switch to the other part of this today's lecture, where basically we will be using R to implement these models which we have discussed in the few last classes, that is the autoregressive, moving average and ARMA model. Thank you for the timing. So let us quickly move to the second part of this lecture.